When the Lyme Disease Foundation was considering the topic for this conference, we wanted to select an area of Lyme disease where progress was needed most. We have all agreed that it is chronic Lyme disease. I was thrilled from the beginning with the opportunity to bring together a group of leading researchers and physicians to engage for 2 days in a fruitful discussion about this rather obscure, controversial, scientifically unclear, and at the present time undefined part of Lyme disease. There were, however, several developments which were to taper my excitement. Once the topic of the conference was announced, I started to get many phone calls suggesting and or demanding what the focus of the conference should be, who should and shouldn't speak, what conclusions the speaker should arrive to, and so on. I have realized that chronic Lyme disease is so politicized and already predefined in the minds of some that it would be almost impossible to organize a scientific meeting with the objective of reaching a consensus about the definition and management of the chronic Lyme disease based on facts rather than personal beliefs. This was confirmed by the fact that several of your colleagues, despite working on the topic, refused to come and present their data for the fear of being politically incorrect. I would like to believe, and I do believe, that we all are here today because we want to find out what chronic Lyme disease is and how it should be managed. We should not forget that in the middle of our uncertainties are patients who are sick. Whether it's chronic Lyme disease or something else, it's not that important to them. All they want is to feel well again. Today, I am excited. I am excited that we were able to gather a group of 30 honest presenters who are here to discuss definitions, research, laboratory, and clinical aspects of chronic Lyme disease with the ultimate goal of reaching consensus in all of these areas. To achieve this, there are a few rules by which the Lyme Disease Foundation conferences are governed. Although open to the public, this conference is for medical professionals, including discussions after the scientific sessions. When asking questions, please identify yourself with your full name and affiliation. A public forum has been scheduled for Saturday afternoon, where the public will have a first-hand opportunity to ask questions. I would also like to ask every presenter to stay on time so we can complete the agenda. We have a timer right in front of here. Can you stand up, Kathy? And she will signal last 5 minutes and time out. Most of all, I'd like to ask all of you to leave your preconceived notions and differences, if you have any, out of this room and engage in an honest and sincere scientific discussion. Before we start the conference, let me thank the Lyme Disease Foundation for creating this opportunity, all companies who supported this meeting, and the conference co-chairs, Drs. Adler, Donta, and Enwald, and certainly the presenters who accepted the invitation to participate in this gathering. Thanks to all of you for attending with the belief that science can and will replace politics. I hope that the next 2 days will prove that it can be done. Enjoy the conference. Thank you. Just very few brief organizational announcements. There have been a chronic Lyme disease conference questionnaires, which I have sent to every physician who registered before April 1st. I would like to ask every physician who did not fill them to do so and leave them at the registration desk. You can pick them up there and leave them. They would certainly help us for the 2 discussion forums which are scheduled for tomorrow. As I have already said, public forum is scheduled for 4:30 Saturday until 6 p.m. Anybody who wants to receive 15 CME credits, category 1, from Mount Auburn Hospital needs to sign in and sign out at the registration desk in the sheets at the beginning and the end of each day. Also, all of you have enclosed the evaluation forms which need to be filled in, and you receive the CME certificate in the exchange for the evaluation as well as the full attendance. I would like to mention that today's lunch sponsor is Smith Klein Beecham Pharmaceuticals. You have the red tickets, have them ready. The lunch is going to be served in the plaza dining room, which is at your at the left from the lobby, and there's going to be additional seating downstairs in State Suite A and B. Today evening we have a reception. Please have your tickets ready for that as well. We will have buses ready for everybody to transport to reception at the Dartmouth Street. That's where you left your cars when you came in. And they are going to be ready for everybody from 6:30 till 7:30, transporting to the reception site, and then from 9:30 till 10:30 back to the hotel. Now let's get to business. Let me announce the first speaker, Dr. Steve Barthold, and he will have a presentation on protective and disease-modulating antibody-mediated immunity to Borrelia burgdorferi antigens expressed in vivo.
Just to save some time throughout the morning session, we'll just give you a very brief announcements of who the next speaker is. You can read in your handout a little bit more detail. We won't go into Dr. So-and-so with such and such and all of that. First slide, in the, of course it's not loaded. So, you got a projection? Anybody there? No? I got it? Okay. That's not mine. But it's a good point. Borrelia burgdorferi is a pathogen of many different species, and humans are only one of those many species. And animal modeling is very important and quite convenient. Borrelia burgdorferi infects laboratory rodents, dogs, monkeys, and we can get a great deal of information out of experimental studies such as this. Could you get the right carousel for me, or the right slide set? The laboratory mouse model is very useful, and I think an extremely valuable model for studying some aspects of Lyme borreliosis. They develop persistent infections routinely, and indeed they have many manifestations that parallel what happens in the condition. In human Lyme disease, patients typically develop disseminated infections with a variety of symptoms, including arthritis and carditis, which curiously undergoes spontaneous resolution, even in patients who have not been treated with antibiotics. And then over the course of many months or years, there are periodic bouts of recurrence. The very same thing happens in the laboratory mouse, albeit in an abbreviated scenario. And we're going to talk about that mouse model and the subtle nuances of what is happening between the pathogen and the host, because the mouse is an immunologically responsive host just like you and I are. All right, forward. Reverse. How do I get the slide to go? You've got two more. There's only one side. She had So that was a mouse with arthritis. One of the complicated first speakers died out all over. Okay, we're over here now. As you can see, there's a mouse with a swollen joint, and they typically get arthritis in the early phase of infection, within 2 to 3 weeks after infection. Now I've got the good deal. Okay, here we go. And within a few days after intradermal inoculation of mice by tick-borne infection or by syringe, spirochetes disseminate, and we can detect their presence in peripheral blood and also invade the joint tissue. We can see that with silver stain. And the invasion of spirochetes into joint tissue coincides with the immediate onset of inflammation. And the joint undergoes very severe inflammation in the mouse. And this is in multiple joints throughout the body. It's characterized by synovial proliferation and infiltration with many leukocytes. But curiously, in the joint, we see a predominance of neutrophils. The very same type of pathology occurs in dogs, in monkeys, in a variety of laboratory rodents, and also in acute Lyme disease in humans. As I said, after several weeks of infection, there is total resolution of that inflammation. This is the joint that was previously inflamed, and there is no inflammation left in this animal. And this is an immune-mediated event, which I'll show you is primarily antibody-mediated. And when arthritis resolves, the spirochetes disappear from the joints, even though the animals are still persistently infected. And over the course of several months to a year of infection, there are periodic bouts of exacerbation in which arthritis recurs, and we can find spirochetes again in the recurrent arthritic lesions. Likewise, mice get carditis, and this is the heart, the aorta, going up here, the leaflets of the aortic valves, and all around here is inflammation. But unlike the joint tissue, the inflammation in the heart is predominantly macrophage-mediated. It has a very different character. For some reason, the same pathogen is eliciting different types of inflammatory responses depending upon the tissue. And more importantly, the bacteria invades other tissues and elicits absolutely no inflammation whatsoever. We find them in urinary bladder, we find them in the skin, we find them in lungs, spleen, liver, etc. And there is no inflammation that equals the severity of inflammation that you see in the joint and the heart. So something very curious is happening, that even though multiple organs are being infected with the spirochete, very different events are occurring depending upon the specific tissues that are involved. As I said, mice remain persistently infected, as do most animal species that have been experimentally inoculated. And there is mounting evidence that a large number of human patients that do not receive antibiotic therapy become persistently infected. In the mouse, the most consistent site for persistent infection is the skin. And when we look at the skin at 1 year after inoculation in a distant site, we see extracellular spirochetes. They're not within cells, they're not hiding in immunologically privileged sites. In fact, the skin is a highly immunologic organ. And we see no inflammation associated with the presence of the spirochete. And yet, if we take these organisms out of the skin in the form of a biopsy and transplant that into another mouse, or if we culture these spirochetes and inoculate another mouse, those spirochetes are fully pathogenic and cause disease. So this tells us the immune response is no doubt causing these spirochetes to, or putting them into abeyance, but in the absence of an immune response in a naive host, they're capable of disseminating and have full virulence. Well, another point of introduction with this model is the skin mouse. Mice with severe combined immunodeficiency lack an acquired immune response. And because of that, they cannot clear spirochetes from joint tissue. And what happens in these animals is there's exuberant proliferation of synovium and severe inflammation to the point that this totally takes over the joint lumina and they become severely arthritic. They develop progressively severe arthritis. And in this exuberant synovium, we see many spirochetes. This is one that's curled up here with silver stain. All of these little black tips are the ends of spirochetes that are coursing in and out of the plane of section. There are myriads of organisms in this arthritic tissue. But if we look at other tissues of the skin mouse, we don't see that. There is not a preferential proliferation of spirochetes. In fact, in the heart, they do not develop progressively severe carditis. It kind of stays the same. If we look at other tissues, we see about the same relative numbers of spirochetes in skin and other tissues as we see in an immunocompetent animal. So something special is occurring in the context of joint tissue that this spirochete likes. And something special is eliciting inflammation differentially within the joints, and something special is happening that allows immune-mediated clearance of these spirochetes from joints, but not other tissues. Well, in 1983, Alan Barber described an abundant outer surface protein called outer surface protein A, which was expressed by spirochetes in the midgut of unfed ticks. This is a fluorescence micrograph of spirochetes labeled with OSP-A antibody that Sam Telford took at Harvard School of Public Health. He also showed that this protein was abundantly expressed in culture. But we now know that Borrelia burgdorferi shuts down or ceases the production of outer surface protein A when it is in the host. And so most patients don't seroconvert to outer surface protein A, even though in culture and in the midgut of unfed ticks, it's a very dominant immunogenic protein. There's some published work that's come out in the last couple of years. Alan Barber's older work showing that it's heavily expressed in ticks and culture. And then last year we showed that in the host, you can immunize mice against outer surface protein A and protect them against tick-borne and syringe-borne challenge. But if you challenge them with host-adapted spirochetes, that is spirochetes that have already shut off OSP-A in the context of the host, and you can do that by taking transplants of tissue, ear tissue or skin tissue, from an infected animal that has host-adapted spirochetes, and challenge the mouse by transplant with small pieces of tissue. And when you do that, these host-adapted spirochetes that do not express outer surface protein A disseminate in the host and develop and produce full-blown disease, telling us that OSP-A is not relevant within the mammalian host. The spirochete is not expressing it, and it's not vulnerable to very high titer immune response to OSP-A. Likewise, Aravinda De Silva at Yale showed that in ticks that were feeding on just regular non-immune hosts, that outer surface protein A was abundantly expressed in the midgut of unfed ticks, but within hours of feeding, commencement of feeding, outer surface protein A rapidly ceases in the spirochete as they migrate from the gut wall into the salivary gland. And so it turns out that spirochetes actually do not have outer surface protein A already in the feeding tick as they are about to enter the mammalian host. OSP-A probably plays a role in its life within the tick, but has no relevance to life within the host. And so the message is that we need to consider the adaptive state of spirochetes and in interpreting how we approach immunity, vaccine strategies, therapy, etc. And as I pointed out with outer surface protein A, spirochetes in culture are abundantly endowed with outer surface protein A. In the tick, in the unfed tick, OSP-A is there. In the feeding tick, it shuts off. And in the host, whether it be a mouse or a dog or a person, outer surface protein A is not relevant to the spirochete. Likewise, we see other shifts in proteins of this spirochete. It's a very dynamic organism. It's not static whatsoever. We see upregulation of outer surface protein C when ticks begin to feed, and we see upregulation of outer surface protein C when spirochetes are within the host. And likewise, there are many other energies of Borrelia that we've yet to discover that seem to be expressed exclusively within the host and not within culture, and possibly not within the tick. Well, how do we get at this? Well, we can use the mouse as a means of approaching which antigens and identifying which antigens might be important. And we know that from the work of our own lab and others, that if you transfer serum from infected mice, whether they be infected by tick transplant or low-dose syringe inoculation, The serum from those immune mice, which we call immune serum, transferred to naive mice, will protect those naive mice against challenge inoculation. In fact, that protective effect is very, very powerful. In spite of the fact that these animals continue to be persistently infected, telling us that these hosts mount an effective immune response to Borrelia burgdorferi, but they're incapable of clearing their existing infection. They can protect other animals, but they can't eliminate their own infection. If we transfer immune T cells from these animals into skid mice, T cells in and of themselves will not protect the skid mice against infection. Likewise, the transfer of immune serum, as we'll show you, will selectively cause arthritis resolution in skid mice with ongoing disease, but transfer of T cells has no effect upon their arthritis. And so there's a great deal of activity to compartmentalize the serum, and as a scientist, this allows me to, or it facilitates the search by using antigens, antibodies, and serum to identify which antigens are driving these important biological functions. Well, if we look at the immunoblock response of animals infected with terminal dilutions of spirochetes grown in culture, and this is an important element. Remember, OSPA is abundantly expressed by spirochetes in culture. So if we use high input doses of spirochetes, the host will respond to outer surface protein A. However, if we use terminal dilutions of inoculum down to 10 to the 1, we find that animals that are actively infected, which is this blot on the right, and ones that didn't get infected, the one on the left, we see strong seroconversion in the early course of infection to outer surface protein C, P39, and flagellum, and not outer surface protein A, which should be right in this region here. We see the very same immunoblock response in mice infected by tick-borne inoculation and with host-adapted spirochetes by transplant. And so this makes life relatively easy. Surely these antigens must be important in biologic activity such as protective immunity and arthritis resolution. Well, just to emphasize the power of this immune serum, if we take as little as 50 microliters of 90-day immune serum from mice infected with 10 to the 2 spirochetes, and transfer that into other naive C3H mice, and then challenge them with increasing doses of syringe-borne organisms, we can protect them with up to 10 to the 7, if not greater, challenge doses of spirochetes. Likewise, if we passively immunize adult or infant mice with 10 microliters of immune serum, or serial full dilutions of that serum, 10 microliter aliquots of those dilutions, we can get protection of adult mice with 10 to the 4 or 10,000 spirochetes with dilutions of up to and including 1 to 40. And in smaller infant animals, we can dilute that serum all the way to 320, which calculates out to 0.3 of a microliter of undiluted serum, which is an incredibly small amount of serum to have this absolute protective activity in these passive immunization experiments. Likewise, if we take skid mice without an immune response, infect them, and let them develop arthritis, and then passively immunize them with immune serum from immunocompetent mice, we can selectively induce arthritis resolution. This is the joint tibiotarsus of a skid mouse treated with normal mouse serum, and it has extensive inflammation throughout the area. This is the heel joint of the Achilles tendon. All of this blueness here is inflammation of the tendon, the synovium, lots of inflammation throughout the section. In contrast, in the very same study, this is a skid mouse that's infected that has virtually no remaining arthritis because it was treated with 90-day immune serum from an immunocompetent animal. And the contrast between this mouse and the previous mouse is spectacular. The immune serum just totally ablates the inflammation that occurs in the joints. However, in the course of those studies, a curious phenomenon began to evolve. And in spite of the fact that transfer of immune serum into skin mice with active ongoing infection and disease induced arthritis resolution, the animals continued to be infected, which is not surprising because immunocompetent animals from which the immune serum came are persistently infected. So passive transfer of immune serum has no effect upon the status of infection. In fact, it has no effect upon circulating spirochetes. That virtually all of these animals remain spirochetemia, in spite of the fact that they receive fairly high doses of immune serum throughout the course of the study. We've tried to overcome this with even higher doses of immune serum and cannot avoid the continued spirochetemia. Also, we could not influence the carditis, so that immune serum had the selective effect on eliminating spirochetes from joints, had no effect on the course of carditis or inflammation of the heart in these animals, and had no influence on circulating spirochetes. Very compartmentalized effect. We've done the same thing with adult C3H mice with an abbreviated treatment schedule because C3H mice, of course, are immunocompetent. And so if we accelerate the treatment schedule, we still can see the same effect. No effect on infection, spirochetemia, or carditis, and yet this dramatic effect upon arthritis with clearance of spirochetes in the joint tissue. Well, what's happening? Which antigens are involved? As I pointed out, if we look at the very early immune response of these infected animals, whether it be by tick or low-dose syringe inoculation, there's a limited repertoire of reactivity to outer surface protein C, P39, and flagellum. And one would surmise that one of these antigens is likely to be involved in protective and/or arthritis-resolving activity. So we made recombinant forms of proteins of each of these outer surface protein C, P39, and the immunodominant portion of the flagellum molecule. It shows a portion of flagellum because it's not soluble, and the fragment is soluble, which makes life a little bit easier for us. Just walking you through this slide, we have a GT control group. These are mice that were passively immunized with hyperimmune serum to a control antigen, glutathione transferase. They got serum 50 microliters at each of these intervals with no effect upon infection, disease, etc., as you would expect. Another control group was mice receiving 90-day immune serum. That is, a serum for mice that are actively infected with low doses of spirochetes. And a single dose at time 0, as we pointed out, protected the animals against infection, and obviously they did not develop disease. And when we transferred immune serum at 8 days after arthritis was already underway and the infection was fully disseminated, we could not influence arthritis or infection or spirochetemia. We selectively induced arthritis resolution, but could not invoke an effect on carditis. With each of these anti-serum to each of these recombinant proteins, we saw essentially no effect. No protection, no effect upon arthritis. And yet that's all the immunoblock responded to. Those were the only antigens that were present in the early immunoblock responses. So this is basically a negative experiment, and we can conclude that something went wrong for a variety of reasons. And of those of you that are probably familiar with the literature, others have shown that outer surface protein C is protective. If you immunize mice or gerbils against outer surface protein C, you can protect those mice against challenge inoculation. We failed to do that. Well, we went back and reinvented the wheel and generated a recombinant form of OSP-C from a strain of Borrelia burgdorferi that Bettina Wilski showed protection with, and that was PKO. Making a recombinant form of PKO OSP-C and immunizing mice with that antigen, we passively immunized mice with PKO OSP-C antibody, and lo and behold, we found protection. And yet, it had no effect upon existing infection, spirochetemia, or disease. These are not absolute results because PKO is less pathogenic or virulent in 40s or studies. But this validated the fact that our recombinant proteins are probably appropriately immunogenic. It's just that there's something different about the strain of Borrelia that we're working with. Indeed, outer surface protein C of N40 is buried in the outer membrane and not surface exposed, whereas the PKO OSC is surface exposed and is vulnerable to the effects of antibody. We've shown that in vitro as well as in vivo. So different strains of Borrelia may or may not express outer surface protein C, and may or may not express outer surface protein C on its outer surface, which are going to result in variable responses. But it still didn't incriminate the antigen that we were after that's causing protective or arthritis-resolving immunity. Well, going back to the skin mouse joint tissue, we can label spirochetes in the context of that proliferating joint tissue. Here is a spirochete here, labeled with serum from an immunocompetent, actively infected mouse, labeled with immune serum. So this is an indirect immunoperoxidase assay, and spirochetes readily labeled with immune serum from other infected mice. And yet we could not label spirochetes in serial sections in which we knew spirochetes were present in the tissue with anti-sera generated against heat-killed spirochetes representing antigens of spirochetes in culture. We could not label spirochetes with anti-serum outer surface protein C, P39, and we could only weakly label them with anti-serum from flagellum. So that suggests that some other antigen must be responsible for this labeling, possibly the target for the arthritis-resolving immunity that we're after. Well, in the last couple of years, there's been a wonderful revolution of recognition in that Borrelia burgdorferi indeed is a dynamic organism, and a number of laboratories are now showing that there are antigens of Borrelia burgdorferi that are selectively expressed in vivo, that is, in the context of the host, and not in culture. And so immunoblots of Borrelia burgdorferi, which are generated from cultured organisms, are not going to have the antigen that we're after, and therefore antibody is not going to react against it. And these various laboratories, including our own, have shown antigens of Borrelia burgdorferi that are indeed expressing in the mouse, but not in culture. And if you take those recombinant proteins, you can find that antibody is present that does react against those in vivo expressed proteins. This first paper by Champion and Jim Miller's lab at UCLA was MA. John Suck at Yale described P21. Reinhard Wallach described a protein called PG. And Akins and Justin Radolph's lab in Texas has shown this BBK210. We're finding at Yale a large family of antigens that are expressed in the context of the host. And we have yet to find and incriminate which of these antigens, so far all of the ones that we have tested, do not have any arthritis-resolving immunogenic properties. So the research goes on. But we believe that this is the answer to the paradox, that we're not seeing the reactivity of immune serum that's biologically active against antigens in immunoblocks, and that's because the antigens that we're after are ones that are expressed within the host. Well, one troubling thought before we part, and that is all of this talk about protective immunity may be irrelevant. Because if we challenge, or if we passively immunize mice with immune serum, whether that immune serum is generated by tick, by cultured organisms, or by transplant with hosted out with spirochetes, as I pointed out, that immune serum is very powerful in protecting against syringe-borne inoculation. We get no infection, no disease. However, when we passively immunize mice with large volumes of immune serum, and Sam Telford has gone to great extremes to overwhelm the mouse with huge volumes of immune serum, we see basically no protection against infection. The immune serum that is protective against high doses of syringe-borne organisms has no effect against tick-borne incoming spirochetes, and yet induces arthritis resolution in the host, but does not influence carditis. Likewise, animals immunized with immune serum and challenged by transplant are not protected against infection. They don't get arthritis, but they do get carditis. And so, spirochetes may very well be shutting off all of these immunologically vulnerable antigens within the tick or in the process of entering the host, and those antigens are not available for immune-mediated clearance, except perhaps in the context of joints. Just one final slide emphasizes what I said. If we generate immune serum from animals infected by syringe, tick, or transplant, that immune serum will protect mice against syringe-borne challenge. We're in the process of filling in these question marks, but I predict that they will all be negative. The immune serum has no effect upon host-adapted spirochetes coming into the host via the tick bite or coming in via already adapted spirochetes. And yet, this immune serum generated from all of these forms of incoming organisms is capable of inducing arthritis resolution. So we have a long ways to go, but the mouse model is telling us some very subtle, or is explaining some very subtle nuances of the host-parasite interaction, and it's not going to be a simple story. My next speaker is Ronald Shell, who is the chief bacteriologist at the University of Wisconsin State Laboratory of Hygiene and professor of medical microbiology, immunology, and medical school. And with that, take over.
Can you hear me all? Can you hear me well? Is this small microphone on? It's not. First of all, I'd like to thank the Quashioners and the Lyme Foundation for the invitation to speak here. It's very important. If you get a chance, also look at the journal. The journal came out this month, enumerating a lot of things that Mario Felipe and myself and Steve Bartlett have done on the Lyme models. So it's very important to look at it. What I would like to do today is I've got a sort of a written talk. I used to give an oral presentation, but I decided to calm down. I usually wander a lot around the audience. Anyhow, what happens is I'll give you an oral presentation written that focuses on a model that we look at in terms of severe destructive arthritis and try to relate it to how it may in fact relate to vaccination and some side effects that may occur. There is strong evidence that T lymphocytes participate in developing chronic Lyme arthritis. CD4 T lymphocytes are the dominant T lymphocytes isolated from the synovium of Lyme arthritis patients. T lymphocytes also respond vigorously to stimulation of Beta-Dorfroid antigens in vitro. In addition, specific human CD4 T lymphocyte clones established from patients with chronic Lyme arthritis have been shown to recognize Beta-Dorfroid outer surface proteins A, B, flagellum, and key shock proteins 6B and 7B. Others have suggested that the antibody response to outer surface protein marker A is a marker for critical T-cell lymphocyte response that warms Lyme arthritis. Furthermore, T-cell lines from treatment-resistant Lyme arthritis patients recognize outer surface protein A, but T-cell lines from treatment-responsive arthritis patients rarely recognize this protein. Collectively, these investigations suggest that T lymphocytes play an important role in chronic Lyme arthritis. Can somebody turn the first slide on, please? Okay, that's great. Thank you. approaches have fallen short of proving that T lymphocytes are involved in the pathogenesis of Lyme arthritis. Recently, we showed that severe destructive Lyme arthritis developed in vaccinated hamsters after challenge with isolates of Ecuadoriferæ sensu-lato and suggested a role for cell-mediated immunity. Now, specifically, 5 groups of 3 hamsters each were vaccinated with a formalin-activated Ecuadoriferæ sensu-stricto isolate CD111 and alum. I think you can clearly see the groups that are probably marked. At week 1, 3, 5, 7, and 9 weeks after vaccination, hamsters were challenged in the hind paws with Ecuadoriferæ sensu-stricto isolate C111. I'll enumerate later on, it's irrelevant the isolate that I'm using to challenge. Hamsters vaccinated for 5 weeks or less developed severe destructive arthritis, and that's at very top lines. Swelling was detected 5 days after challenge and increased rapidly, with peak swelling occurring on days 14 to 16 after challenge, before gradually decreasing. The next slide shows the severity of the hind paw swelling detected in vaccinated hamsters compared with controls. Slide doesn't do justice. The animals, I have to describe visually to you that if a hamster paw sits in this direction, that when they get this effect, it not only affects the hind paw, it affects the knee joint or the shoulder, so that eventually the paw goes backwards and the animal is dragging its hind legs on the ground. It affects the front shoulders, and finally the animal is down in the cage and it has to be fed. That's how severe it is. By contrast, hamsters challenged with 5-week vaccination failed to develop severe destructive arthritis. So if you allow them to vaccinate and allow them to develop immune serum, you will not develop arthritis. However, these vaccinated hamsters still develop severe destructive arthritis when challenged with other isolates of the genomic groups of Ecuadoriferæ sensu-lato, which include sensu-stricto, gardneri, and alzalii, despite high levels of isolate vaccine-specific protective release antibody. In general, all seroprotective groups or gene species of Ecuadoriferæ sensu-lato can prime, vaccinate hamsters for developing severe destructive Lyme arthritis. The elicitation of arthritis is prevented only when the vaccines are challenged with the homologous vaccine isolate. Severe destructive arthritis still is elicited in the vaccines with the homologous infection if given prior to development of protective antibody. Hamsters can also be primed, vaccinated for the development of severe destructive arthritis with different preparations of Ecuadoriferæ, including whole and activated spirochetes, live spirochetes contained in alum, spirochetes treated with antimicrobial agents, frozen and thawed spirochetes, and subunits of Ecuadoriferæ. In addition, priming of hamsters with these preparations is not adjuvant dependent. So we can do this with regular human improved alum or adjuvants like voice complete adjuvant, but generally used with alum as it is human improved. We next saw direct evidence that T lymphocytes were responsible for the induction and elicitation of severe destructive arthritis. In which T lymphocytes were obtained from the lymph node cells of vaccinated and non-vaccinated animals by depleting B lymphocytes with monoclonal antibody 14.4S, which recognizes surface cell markers on hamster B lymphocytes. Flow cytometric analysis showed that the percentages of B lymphocytes present in the samples, 24 and 12% for vaccinated and non-vaccinated hamsters respectively, were significantly reduced after panning with monoclonal antibody 14.4S. Now, enriched T lymphocytes from vaccinated and non-vaccinated animals containing only 0.9 and 5% B lymphocytes respectively. Additional experiments with Con-A T-cell nitrogen showed that the enriched T lymphocytes had an enhanced proliferative response at the top. By contrast, the proliferative response after stimulation with LPS, B-cell nitrogen was significantly reduced. So we know that they are enriched T lymphocytes. We next examine the ability of T lymphocytes obtained from vaccinated hamsters to confer abdominally severe destructive arthritis on naive recipient hamsters. T lymphocytes from vaccinated and non-vaccinated hamsters were injected into naive recipient hamsters, which were then infected with Ecuadoriferæ C111 or 297. Swelling was detected 6 days after challenge and increased rapidly, with peak swelling occurring 14 to 16 days after infection before gradually decreasing. By contrast, recipients of normal T lymphocytes from non-vaccinated hamsters developed only slight swelling. The swelling developed slowly, day 10, and was significantly less and of shorter duration than the swelling detected recipients of immune T lymphocytes. Non-vaccinated hamsters infected with Burley-Rudolphi sensus stricto isolate C111 and 297 also developed slight swelling. The swelling was significantly less at day 14 and 16 after challenge than the swelling detected recipients of normal T lymphocytes challenge with isolate C111 or 297. In addition, non-vaccinated hamsters injected with BSK failed to develop severe swelling of the hind paws. Similarly, recipients of T lymphocytes from vaccinated and non-vaccinated hamsters injected with BSK, the so-called perfect control, failed to develop any clinical and pathological manifestations of Lyme arthritis. As further support that T lymphocytes play an important role in developing severe destructive arthritis, we treated vaccinated hamsters with rat monoclonal antibody GK1.5 that recognizes the CD4 molecule on hamster T lymphocytes. When vaccinated hamsters were depleted of CD4 T lymphocytes by administration of the monoclonal antibody and challenged with isolate C111, they failed to develop severe destructive arthritis. That's the lower figures, or lower lines. Similarly, non-vaccinated hamsters with or without depletion of CD4 lymphocytes failed to develop severe destructive arthritis. However, severe destructive arthritis was readily invoked in hamsters vaccinated with the whole cell vaccine preparation and challenged with Burley sensus stricto 297 or C111, which is the red top line. Now, a direct role for CD4 T lymphocytes in the development of severe destructive arthritis is not surprising. CD4 T lymphocytes have been shown to participate in developing rheumatoid arthritis in humans and induction of collagen arthritis in mice. What is surprising is the extent of the CD4 T lymphocytes are, or the extent that they're involved in the development of severe destructive arthritis. Treatment of vaccinated hamsters with monoclonal antibody GK1 completely prevented the development of arthritis. When administration of the monoclonal antibody was discontinued, severe destructive arthritis was easily detected. Now, Kern, Myers, and Nichols, and I have Nichols' name, I apologize, spelled as inserted in the K, have also shown a role for T lymphocytes in the development of arthritis in mice. They show that depletion of subsets of T lymphocytes altered the pathogenesis of Burley-Rudolphi infection in C3H, AGJ, and VLC mice. Depletion of CD4 T lymphocytes enhances severity of arthritis, suggesting that CD8 cells may be responsible for the exacerbation of the arthritis. Although these results conflict with ours, they do demonstrate the importance of T lymphocytes in the development of Lyme arthritis. Now, an explanation may be as follows. The explanation for the difference may be that CD4 T lymphocytes play a greater role in the induction of severe destructive arthritis than they do in controlling the mild arthritis that's detected in young mice and adult hamsters after infection with Burley-Rudolphi sensu-lato. When non-vaccinated hamsters are depleted of CD4 T lymphocytes and infected with Burley-Rudolphi, they develop minor synovitis, basically what Nichols had seen, or Nichols had seen. This suggests that CD8 lymphocytes are responsible for the development of synovitis in non-vaccinated hamsters. Collectively, these studies do illustrate the importance of cell-mediated immunity, specifically T lymphocytes, in controlling and preventing induction events leading to the development of synovitis in non-vaccinated hamsters and severe destructive arthritis in vaccinated hamsters. Several Burley-Rudolphi sensu-lato proteins, including other certain proteins A, B, C, and 39 kilodalton protein, have been shown to kill B. burgdorferi in vitro and induce protection in animals against challenge with the Lyme disease virus. Of these proteins, outer protein A has emerged as the leading vaccine candidate. Presently, outer protein A is being tested for safety and immunogenicity in human field trials. We evaluated the ability of a recombinant outer surface protein A vaccine to induce and maintain sustained levels of Borrelia-slider antibody in humans. Briefly, females and male volunteers were vaccinated with a placebo 1, 5, 10, and 30 micrograms of outer surface protein A. A booster vaccination was administered 30 days after the primary vaccination. I hope you can see all this. The first principle is that Borrelia-slider antibodies correlate with protection. It's the first thing you must understand. We've got 5 minutes of time. Borrelia-slider antibodies were not detected consistently in individuals vaccinated with 30 micrograms of outer surface protein A. If you look, you'll see that we have a sense of their number of patients responding. Borrelia-slider activity was detected in 0, 4, 80, and 81% of vaccinated 60 days after vaccination with 1, 5, 10, and 30 micrograms of recombinant OspA, respectively. Even at the peak Borrelia-slider activity response was 60 days. The titers ranged from 0 to 80, and the cytal activities were low and varied greatly. Only one individual had detectable Borrelia-slider antibodies, and that's way at the bottom at 180 days after vaccination. We repeated these studies in hamsters. When hamsters were vaccinated with 120 micrograms of recombinant OspA vaccine and boosted 28 days after vaccination, a similar Borrelia-slider antibody response was detected. Peak Borrelia-slider activity was detected 6 weeks, and that's the dotted lines going up after vaccination. 2 weeks after booster, and waning very rapidly. Noticing was found very rapidly at week 10. No Borrelia-slider activity was detected 30 weeks after vaccination. When serum was obtained from vaccinated hamsters and humans at peak Borrelia-slider activity and incubated with different seroprotective group isolates, only the homologous isolate B31 was killed. These results were confirmed in vitro by challenging recombinant OspA vaccinated hamsters with 4 different seroprotective groups of Borrelia. Again, vaccinated hamsters were protected only against challenge with the homologous vaccine isolate. These results are discouraging and unimpressive. They suggest that recombinant OspA is a poor image despite the protection for both humans and humans, or hamsters and humans. So although Borrelia-slider activity was induced, the titers were low and Borrelia-slider activity waned rapidly. In addition, the recombinant OspA reduced the Borrelia-slider activity that was restricted to the homologous challenge. Vaccines would not be protected from infection with other isolates of seroprotective groups of Borrelia. To these difficulties must be added the ability of Borrelia to alter its outer surface proteins during attachment and feeding. Schwann and colleagues showed that Borrelia downregulates the expression of outer surface protein A and begins rapid synthesis of outer surface protein C. Even though anti-outer surface protein A serum has been shown to sterilize ticks infected with the Lyme disease spirochete, the period of attachment and level of circulating anti-OspA antibody may be extremely critical for Borrelia-slider activity to occur. If Borrelia rapidly upregulates C while downregulating A, some spirochetes may still survive and be available for transmission to the host. Collectively, these studies suggest that combinations of Borrelia sensilato proteins will ultimately be required for a comprehensive vaccine. The composition of the vaccine, however, is confounded by the immunologic and molecular heterogeneity of the major outer surface proteins that can induce protection against Borrelia. Another concern is the reinvention of Borrelia to develop a comprehensive vaccine. As more and more protective antigens are added to the composition of the vaccine, the ability of these combinations of proteins and other antigens to induce or elicit adverse effects may increase. Likewise, the immunogenicity of these antigens must be proven. An adjuvant may be required to induce and maintain sustained levels of Borrelia-slider antibodies. The vaccine containing adjuvant may also enhance the potential for adverse effects like severe destructive arthritis. In conclusion, the hamster is an excellent model to study the immune response to infection with Borrelia. Subsets of T lymphocytes can be distinguished, and their interaction with other cells can be determined. In addition, the human response of hamsters mimics the antibiotic response of humans to infection or vaccination. More importantly, the hamster's propensity to develop adverse effects, specifically severe destructive arthritis, is an effective way to define the antigens responsible for arthritis and evaluating vaccines for adverse effects. Each animal presents unique opportunities, and they should be explored to obtain a comprehensive picture of the types of responses humans may develop. Thank you.
Speaker is Dr. Mario Lee, who is Senior Scientist and Chairman of the Department of Parasitology at the Lyme Regional Primate Center. No better place for animal modeling.
I just wanted to start thanking the Lyme Disease Foundation for inviting me. I'd like to be very pleased to have the first slide because I am responsible for that. And you know, this is Stephen Roberts, the first slide. I have been asked to focus on a review of the rhesus monkey model for Lyme disease with a focus on chronic Lyme disease, which is the subject of this meeting. I will very relatively refer to data that are already published, but also some data about interest in the talk that are new. And those pertain to the issue of neuroborreliosis. My colleagues in this study are Dr. Roberts, a pathologist, Dr. Lowry, medical entomologist, Dr. John England, neurophysiologist of New Zealand State University, who joined our group recently as a collaborator. Dr. Violet Dennis, immunologist at Tulane, and Skip veterinarian. Just as a technical reminder, most of our, in fact, all three of the infections that we have performed in rhesus monkeys were done by means of ticks inoculated initially or infected initially with the JD1 strain of Borrelia burgdorferi, which is the Borrelia burgdorferi syncytial isolate. We do this by means of the tick capsule, and this is just the engorged emerging from the tick capsule after 5 days. I will report data extracted from 3 experiments. Experiment 1, still an ongoing experiment, involves 12 animals, or involved initially 12 animals, 9 infected and 3 controls. 6 of the 9 infected animals were tick inoculated, 3 were needle inoculated. These are the only 3 needle inoculated animals that we have used in these 3 experiments. 3 were controls, as I just mentioned. The duration of this experiment in months, the first phase lasted 48 months, the second phase is still ongoing. Experiment 2 involved 6 animals, 5 infected, and that were tick inoculated, 1 control. And this experiment lasted 6 months. And finally, experiment 3, the shortest of them all, involved 7 animals, 5 inoculated, and 2 controls, and it lasted 3 months. This summarizes the observations that we made in terms of signs of Lyme disease in the rhesus monkey. We observed the migrants, arthritis, neuroborreliosis, conjunctivitis, you name it, we saw it. In most cases, at the clinical level, the numerically much larger extent at the gross and/or microscopic levels. I will refer exclusively to the data that pertain the signs of erythema migrans, arthritis, and neuroborreliosis. And I will bring up erythema migrans, although it does not really refer directly to the issue of chronic Lyme disease, for a reason that I hope will become apparent in a minute. The frequency of appearance of erythema migrans is quite high. Clinically, we observed it in 4 out of 6 of the diplomated animals and 1 out of 3 of the non-diplomated animals in experiment 1. Microscopically, however, it was evident in 6 out of 6 of the diplomated animals and 1 out of 3 of the needle-affiliated animals. And I'll explain in a minute what I mean by erythema migrans as visualized under the microscope. In experiment 2, 5 out of 5 infected animals had evident erythema microscopically. And in experiment 3, 4 out of the 5 uninfected animals had erythema evident at microscopic level. At the clinical level, it was relatively frequent in experiment 2, not quite as frequent in experiment 3. So this is fairly variable, but at the microscopic level, we almost always see it. And what is it that we see? We see, it is also very evident in man, perivascular lymphocytic infiltrates. And occasionally, we manage to also see these repeated structures stained with or evident of a specific monoclonal antibody. The reason why I wanted to bring up erythema as an interesting sign from the perspective of chronic Lyme disease is the following. The perivascular lymphocytic infiltrates seen over and over again in the skin have substantiated the notion that the circulatory system is a port of entry of the spirochete on the brink of dissemination of the infection. But we have also seen perineural lymphocytic infiltrates. Are here. This is a section of skin. These are blood vessels, and you see the perivascular lymphocytic infiltrates. But in B, what you see is a perineural lymphocytic infiltrate, and it is tempting to speculate, and this is why I brought it up, that this may be a port of entry into the peripheral nervous system, perhaps en route towards the central nervous system, or as a localized port of invasion. I will briefly refer to arthritis. In experiment 1, involving initially 9 infected animals, we have now started to look at these animals 4 years into the infection process, and I will show, although here it says not determined, this slide is a little older than the data that I now have, and I will show evidence of what I think is very chronic arthritis, if one may allow that qualifier. Experiment 2 is the one that we already published, which involved 5 animals. And although we only saw arthritis clinically in 1 animal, at the gross level it was quite evident and with incipient evidence of a chronic infection, of a chronic lesion, and the same on the microscopic level. Experiment 3, we only saw arthritis at the microscopic level, and what that means is that we saw synovial cell hyperplasia in all those cases in which this is a normal synovial membrane or a synovial membrane of an uninfected animal, and this is the sort of hyperplastic membrane of an infected animal. In addition, often there are lymphocytic infiltrates and the beginnings of fibrosis. At the gross level, this is what I meant by a lesion that is incipiently chronic. This is lateral erosion of the cartilage, evident 36 months post-infection in one animal out of 5 that were sacrificed. This periarticular fibrosis and fibrosion is very, very marked. There is also some single cell hyperplasia that is residual. Now we come to the issue of neuroborreliosis. This summarizes our observations of experiment 3, the one that lasted only 3 months. And it struck us that most, in fact, all of the signs of neuroborreliosis were evident in the peripheral nervous system. Here are the 2 control animals and the 5 infected animals. We saw necrosis of sensory ganglia, and also root ganglia in all of the infected animals. More importantly, we saw peripheral neuritis, often accompanied by perivascular lymphocytic infiltrates of many of the peripheral nerves observed in all animals, here and here. An example of this peripheral neuritis is observed here. This is one of the animals participating in experiment 3. You can see the markers of structural disorganization of the axons in this peripheral nerve. Because most, well, let me just backtrack 1 second. We have a similar table that I don't want to show because it is just too many tables, of experiment 6, which is, experiment 2, the one that lasted 6 months. And the table is very similar. Most of the evidence is that peripheral nerves are involved, with one exception, in which we see fibrosis of nerves within the spinal canal. Because of this emphasis on the peripheral nervous system, we got together with John England of the Department of Neurology at LSU and designed a protocol to try to look objectively by nerve conduction studies at these at the possibility of pinpointing in that way whether the peripheral nerve system was involved in the animals of experiment 1. This experiment started 3 years into the infection process. We looked at 8 infected animals, 8 of the 9 infected animals, and 3 controls on which we performed clinical exams to try to see if peripheral neuroborreliosis was evident clinically. We did electrophysiological studies not only with 3 uninfected animals, but also on 7 additional normal animals to establish a solid baseline nerve conduction study data, and also on the 8 infected animals. And I'll explain in a minute what we did in terms of electrophysiological studies. We did biopsies of 4 infected animals and 2 controls of the serum nerve when we thought it was pertinent in terms of the results of the electrophysiological studies. And we necropsied 1 year after the study was initiated, 5 infected animals and 1 control. Clinically, only 1 animal showed signs of peripheral neuroborreliosis. And this is a marked atrophy of the gastrocnemius muscle in animal J748. By the time this animal was sacrificed, this lesion had reverted to normal. And this is a recurrent theme in our study, that what we observed for a period of weeks eventually returns to normal. The nerve conduction studies were performed both on local nerves and on sensory nerves. Just a brief methodological interlude. Recording electrodes were placed subdermally over the appropriate hand or foot muscle. Caudal surface nerve stimulation was performed both distally and proximally. And we looked at 3 motor nerves, median, ulnar, and tibial. And those responses in terms of amplitude were recorded, and the conduction velocity was calculated. We also measured distal latencies. On sensory nerves, we used recording electrodes placed over the nerve, median or ulnar, at the wrist, and sensory nerve fibers were stimulated with digital electrodes. On the left-hand column, you have the list of animals involved in the study. These three first animals are the control animals. We had 1, 2, 3, 4 tick-inoculated animals and the 3 needle-inoculated animals. We observed changes in the amplitude of the response in all of the animals, and that change is consistent with axonal loss. Only in one animal we observed a change in the velocity of the nerve conduction velocity, and also in the distal latency. And that, in combination with the reduction of the amplitude of response to this left ulnar nerve, entailed that in addition to axonal loss, there was demyelination. And this is an example of axonal loss in one of the sural nerve biopsies. This is the control animal, and this is a section showing the normal number of myelinated nerve fibers versus a markedly reduced number of myelinated nerve fibers. And that is what it refers to as axonal loss. And this was quantified by Don Roberts using morphometry on the sural nerve biopsies. And here is the list of the animals that were biopsied. 2 controls, 2 needle-inoculated, and 2 tick-inoculated. And you see the number of myelinated axons in the controls is here. You see a reduction of the number of myelinated fibers in the axons. And here is the level of significance of such loss. This is the figures on the left-hand side depict the ratio between the nerve section area and the axons that retain myelin. And so you see an increase in the ratio when this number is diminished, and on the right-hand side is the standard deviation of that ratio. In 2 animals, J748, the animal that also showed the tibial nerve involvement through atrophy of the gastrocnemius muscle, this is significantly diminished, or therefore the ratio is significantly increased. And in J200, the tick-inoculated animal, there is also a significant decrease in the number of myelinated fibers. One of the really remarkable features of the data collected over 13 months is that the nerve conduction attributes return virtually to normal by the time of necropsy. And one of the evidence, one of the indications or consistent with that return to normal that we saw in necropsy was regenerative changes, which I showed here as an example in J748. This is a tibial nerve that innervated the gastrocnemius muscle in the animal with atrophy. You can see regenerative changes throughout the section. And I have summarized those data in this table. Here, this is neuroborreliosis and peripheral nervous system 48 months post-infection, experiment 1. These are necropsy summaries. And really what you see in peripheral nerves, median, you see regenerative changes. Again, fibrosis in some cases, neuroma, all of which are regenerative or evidence of regeneration of the axonal loss. So this is a summary of our study on nerve conduction of the peripheral nervous system. What we see is mainly axonal degeneration. Only one distal neuronal lesion had probable demyelination, and we see see widespread axonal regeneration and recovery. What about the central nervous system? Well, we did see 48 months post-infection signs of meningitis in 3 animals. Cerebellum and the spinal cord. But this is actually relatively minor compared with the widespread lesions that we saw in the peripheral nervous system. This is what I described as meningitis in animal K167, which was needle inoculated. And this is in the equivalent in the choroid plexus of that animal. And you can see if you compare this with the pattern in a normal animal, you can see how this is markedly modified. Now, I think the most important question that one can perhaps ask concerning the initial question that one can ask concerning the pathogenesis of the conditions that we have seen is whether the animals are still infected or not. Question number 1. Question number 2, are the live spirochetes in the wings, or are they only their residual antigens eliciting perhaps an inflammatory response? We were able to culture spirochetes from all of the animals involved in experiment 1 within the first 10 weeks of infection, both from the blood and from the skin. But it sacrificed from none of the tissues that we cultured, we were able to recover spirochetes. We have not yet completed, in fact we haven't yet started the PCR analysis, but PCR analysis will give us evidence of DNA presence, but not of presence of active infection. And as I said, we were unable to culture spirochetes from the tissues. Now, circumstantial evidence of active infection is provided by these longitudinal western plots. This is J415, an animal participating in experiment 1. And you can see that over a 1-year period, this is a scale in weeks, this is the first week of infection. The first year of infection, you see a gradual increase in the number of bands present. In over a year of infection, you see new IgM bands appearing. And 2 years after infection, you see even more bands present in the IgG section, and you see new bands that are still appearing in the IgM panel. Finally, over 200-week period, the 4-year period the experiment lasted so far, we titrated P39 in the serum of one of the animals, and we observed no significant decline in the titer to the P39 antigen. In conclusion, chronic Lyme disease may be investigated in the rhesus monkey. Neuroborreliosis, which is unique to the rhesus model, is manifest chiefly in the peripheral nervous system. This may be a characteristic of the JU1 strain of Bepodopteran used in this study, or perhaps a trivial consequence of the fact that the CNS is not persistently monitored by us. Therefore, the current work is directed to investigate the incidence of neuroborreliosis of the CNS using a strain of Bepodopteran isolated from the CSF of the patient, and this was provided to us by Pat Coyle. We will also investigate some other sensory, visual, and auditory potentials in order to, and we will measure that longitudinally in the 5 animals that we infected with these putatively neurotropic strain, and also in 3 animals that we newly infected with the JU1 strain, 8 animals in total and 1 control. And it is our hope that we may verify that the predominant involvement of the peripheral nervous system in our original study was perhaps due to a strain-dependent phenomenon, but that is obviously another question. Thank you.
Have you tried putting immune serum into control animals to see if they will develop or T-cell mediated, see if trying to press them with infection related or immuno-related?
We have done passive transfer of immunity studies, but only with the purpose of investigating the Osprey vaccine. We have not looked to see if passive transfer of immune serum would elicit any level of pathology. We are really not able to do cell transfer experiment because these animals are not inbred.
Speculate on what you think is responsible for the enduring reaction.
Yes, I certainly do that. And unfortunately, it will be only a speculation. But this is not my speculation either. Many other people have brought this up as a dual possibility, or as alternative possibilities. The lesions are elicited by living spirochetes, on the one hand, or by responses to residual antigen of dead spirochetes. My thinking, in this very simplistic interpretation of what is happening, is that both are probably true. We have much more evidence of presence of spirochetal antigens, but that is only because we look for spirochetal antigens in our sections by immunohistochemistry, and when we see something that appears to be positive, we cannot discern whether this is a live or a dead spirochete. One of the things that we would very much like to do, and we will do this ongoing experiment at the time of sacrifice, is to culture massive amounts of tissues to see if we can pinpoint with absolutely indisputable evidence that the spirochete is present in the lesions. We have not yet attempted what we think is a really involved tissue culture experiment involving many hundreds of tubes. Hopefully that will provide evidence that the live spirochete is present or not in the lesions, and that obviously will dictate or will have importance concerning what sort of therapy is probably effective.
Just one question for Dr. Bartle. Steve, do you have any idea why then with time the phosphate is downregulated following the infection, the initiation? Why do patients do respond with 31 response? And that usually takes a number of months. In my experience, that's an indicator that they've been infected for more than a year or so.
Yeah, that's a good question. The same thing happens in mouse and dogs as well. Eventually, over the course of months, the host eventually seroconverts to outer surface protein A and B. And also, it's been shown that seroconversion occurs at the onset of prolonged recurrent arthritis in some patients. We don't know the whole story. I believe what is happening with this spirochete, this is conjecture only, is that it shuts off its vulnerable antigens on its surface as a survival strategy. Justin Randolph has called this stealth bomber effect, in that it's not logical that a persisting organism would be immunogenic as a survival strategy. But if you take its lipoproteins and you inject them into the skin, they elicit inflammation. They're quite inflammatory in nature. And so it's not logical that spirochetes would have outer surface proteins expressed in vivo and elicit a lot of inflammation. But what we're seeing is you can label spirochetes in the context of joints, and they do seem to be expressing antigens, and they do seem to be vulnerable to immune response. What we think is happening is that spirochetes, for some reason we don't understand, when they get into certain tissues, such as joint, express antigens, surface antigens, become vulnerable to immune clearance, and in so doing also stimulate immune response to antigens that we see on immunoglobulin. I think over the course of many months, this is not a terribly intelligent organism. OSPA also is leaking out in that process in small amounts. We have a gradual and slow immune recognition of certain antigens like OSPA-ASB, which are kind of byproducts of that general process of expression. And eventually, you break over the threshold for detection of antibody. I don't know if that's true or not. We have ways of how we're going to be getting at that, but it is an interesting paradox. It doesn't make sense for survival of the organism for us to express OSPA in vivo, but apparently it does under some circumstances. That's kind of a long-winded response to a complicated question. Other questions?
Schraubing at Cornell University. I have two questions for Dr. Scherm. The first question would be, you placed the CD4 positive cells in an important role for the arthritis. Did you look, or did you characterize the CD4 positive cells into Th1 and Th2 so that we know in which direction it goes? And the second question would be, we had seen in the first talk that skin mice develop an arthritis without any functional T cells. Can you speculate how it can happen that these animals develop arthritis?
The first one, we have not yet broken the CD4s into their subclasses, Th1 and Th2. Okay. We have one obstacle in the hamster, which we don't. Steve has better chance of because he has markers for many interferon, IL-2, IL-4. Hamster, we don't have that. What was the second part of the question again?
Just in connection with the first talk that we have arthritis in the skin mice and functional T cells.
We have a paper coming out on infection immunity that might relate to what you've seen, that it may be also macrophage induced. That will be in the June issue, I think, or July issue of infection immunity, showing that macrophages can also transfer the effect once they process Borrelia burgdorferi, which probably suggests that they become pro-inflammatory, releasing cytokines that start the process off, and the T cells end up helping, but they're not the primary role.
Phil Baker, the NIH. I have a question for Dr. Walker. Well, would you comment on the role of antibody isotype in the various activities you've looked at? And what the role of adjuvant, the choice of adjuvant used, how that might influence the results? I have my feeling that maybe the arthritic effects that might be predominantly against the arthritis might be doing blocking, but not necessarily by bacterial silos. Possibility.
That's quite possible. If you look at the isotype response of mice infected by tick or low-dose syringe, all classes of isotypes are recognized, 1, 2, A, 2B, 3, etc. All I can say is that we can compartmentalize the effects of IgG in that we can induce passive protection and arthritis resolution with the IgG component, excluding IgM. So that's as far as we've gone with that question.
Would IgM would be more bacterial silent?
Right.
Could you imagine so that if you get a predominant IgG response, you might see good expression, good resolution of the arthritis when not necessarily bacterial silent.
We don't know what the mechanism of the arthritis resolution is, but we do know that the spirochetes go away when you passively immunize. These are questions that need to be resolved. Is it direct or indirect effect?
There seems to be also an underlying thing that immune serum or serum that generally when you get infected with Borrelia burgdorferi can induce arthritis. That's not true. Immune serum does not do it. It's the T cell function and macrophage function.
have one question for Dr. Shell. You mentioned that you tried to break down Borrelia burgdorferi subunits to determine what might be driving this discovered arthritis. Have you made any progress in that regard?
Yes, we have. We reported to Alan's theater. Alan was quite interested in order protein A in the presence of an adjuvant would do that. It did not do that. However, order protein A in combination with other order protein A's and with other certain proteins does induce arthritis.
The other observed proteins being extracts of organisms.
No, recombinant.
Oh, recombinant protein. Any other questions? The light is on, things well now. We pass on to Alan Harvey.
It's my pleasure to introduce Dr. Alan Barber, who will be chairing the session, Pathogenesis of Chronic Lyme Disease.
Thank you, Dave, and I want to thank Martina and the other organizers for the invitation to speak here. I hope to bring you up to date on some work that I reported on last year's meeting, and also to extend our observations. I would probably was a little ambitious in what I said in my abstract, as brief as it was. Just didn't have enough time to talk about intracellular organisms. So I'll make a few remarks on that. I think the focus of the meeting on chronic Lyme disease is very appropriate, because clearly that's a great deal of controversy about that, and probably that's the least understood aspect of Lyme disease present. And I don't think anybody says it's a simple explanation, and that's why we're all here, is to delve into the various aspects of this and consider the different possibilities. This shows one case in which we call chronic Lyme disease of someone in Germany who had the erythema vitamins lesions, had pains down to the limbs, and then the actual signs in neurologic disease and meningitis. So the question is how this happens. I think it's generally accepted that in many of these patients at this point in time that they have a very brisk antibody response to the organism, and yet the patient remains ill and gets sicker. So I've outlined a few possibilities here, and I'm going to deal with two of them. This is deal with two of the possibilities. These are possible explanations of how the spirochetes of Borrelia species might persist in the vertebrate host. One is they may be fully immunogenic. That is, that the host immune system does not recognize their presence. And I guess a corollary to that is that something that is not put up there distinctly, but I think that Dr. Alvar is going to deal with, is somehow that the spirochete subverts the immune response by modulating or controlling it, steering it in another direction that's less effective against the organism. A second possibility is hierarchies undergo antigenic variation, effectively staying one step ahead of the immune system. I'll be talking about one example of that in the relapsing fever. Some spirochetes may persist in intracellular locations, thereby avoiding the humoral arm of the immune system, and also to some extent the cellular immunity as well. And at this point, this is fairly controversial. There is some in vitro data indicating this, and clearly if the organisms are going to leave the blood, go into the nervous system or other tissue, for instance the eye, they have to pass through cells. So probably at some point in time the organisms are inside cells. And what is controversial is how long they're there, how long they persist there, and what other types of cells they may be in. And so some of the speakers will be dealing with that. The other possibility is some spirochetes may gain access to niches in which the immune system has less ready access, and that's the second topic I'll be dealing with. And finally, there's the quite speculative possibility that it isn't so much the spirochetes are persisting, it's the nucleic acids. I think certainly the studies from Dr. Garon and his colleagues at Rothman Laboratory show that the spirochetes are secreting or releasing blebs that contain nucleic acids, and in fact, as far as I know, ribosomes. So these continue to produce proteins, and yet, technically speaking, there is not an organism there. So what we'll be talking about a group of organisms in the genus Borrelia. I'm just to orient you to what I'm talking about here. These are all the selected spirochetes. The spirochetes are a separate phylum of bacteria. They're like, they're very different from other bacteria. They have their own phylum. And here are the cause of syphilis. And here's a group of Borrelia. We have Borrelia burgdorferi, related species in the Lyme disease group. And here are some agents of relapsing fever. I'll be talking about the agent of spirochetes in birds. And these are two new spirochetes that have been identified in ticks. Miyamoto has been identified in Japan, and Monstari has been identified in Anthidium americana, the Lone Star tick, in eastern United States and southwestern United States. But I'll be concentrating on these two agents here and how we study those, and perhaps they have some hints on and implications for Lyme disease. So I said I'll be concentrating on two things. First is antigenic variation. Now, that's a way for the organism to stay one step ahead of the immune system. And for that, we study the relapsing fever agent Borrelia in immunocompetent animals. We want to see the immune system working in this case. Now, in terms for our studies of gaining a niche, and the brain in particular, because it's our feeling that entry into the brain is a very important part of persistent Lyme disease, persistent Borrelia infections. There's a clear precedent of that from syphilis. I think it's well accepted that many of the disastrous consequences of getting syphilis were because the organism entered the brain and persisted there despite a very vigorous immune response. So for that, we study, what's gone on. For this, we study another relapsing fever isolate in the immunodeficient mouse, because in that case, we don't want to have a complication with the immune system. Now, how is this relevant to Lyme disease? Well, for one thing, the small BMP proteins of relapsing fever Borrelia species turn out to be homologous to the OSC proteins of Lyme disease Borrelia. That means they're related, and I'll show evidence of that. The OSC proteins are the major surface proteins expressed in the host, as Dr. Barkle and others have pointed out. And they're probably, in that case, under immune selection pressures. OSC proteins are highly polymorphic, highly different from one another, very much like the BMP proteins. Now, more recently, Dr. Norris and some work from our lab demonstrated that genes that are homologous to other BMP proteins of Borrelia parasite also been found in Borrelia burgdorferi, and these may be expressed more commonly in vivo than they've been noted in vitro. And the second aspect of this is that certain serotypes of Borrelia burgdorferi reliably infect the persistent brain of mice. This occurs sporadically and transiently with Borrelia burgdorferi. Now these are the BMP proteins I was talking about. This is Borrelia hermsii. You have small BMP proteins, and you also have large BMP proteins. This is the flagellum. This is a group of Borrelia burgdorferi, sensu-lato, so this would include Guerini and Axilla 2. And this is OSPA B, and this would be OSC. So these OSC is a similar size to small BMP proteins of Borrelia hermsii. The OSPA and B are about the same size as large BMP proteins. This shows the sort of family tree, that relatedness. Here's OSPA and B up here. They're fairly closely related. These are some large BMP proteins of Borrelia hermsii, and these are small BMP proteins. And you can see that the small BMP proteins of Borrelia hermsii are more closely related to OSC than they are to other proteins in the same cell. This is a couple of cases of Lyme fever, what we'll be talking with for a while. And these were two Boy Scouts who got infected up by Spokane. Shows when they were bitten by the ticks and the course of disease. And this was noted early on, decades ago, as being an example of antigenic variation, that if you took organisms here or here, they were different serologically from organisms that first infected these people. This is one of the classic examples of antigenic variation. So you can start this with a single cell. You're not selecting from a mixture that was originally used to infect the animal. A single cell will do this. So all variation is occurring in a clonal population. And first you may have serotype 7, and then by that time there's a large enough antigenic load that the immune system responds to serotype 7. A few days later that's eliminated, but serotype 21 has started to appear here, now is taken over. And that goes on and on for up to 10 different relapses. Now, the way I can think of this is that these proteins, these BMP proteins, the proteins that confer the antigenicity, the serotype identity, can be thought of something like these snails. They roughly have the same shape, but they have different colors, they have different flavors. And so the immune system is just looking at the colors. It doesn't recognize the whole shape of the snail. Because what the immune system recognizes is fairly small parts of proteins, not the whole protein itself. And equivalent to the snail shell, we have proteins on the surface of the Borrelia. And this is probably difficult to see from the back, but basically it shows the N-terminus of several BMP proteins. And these are all like the proteins of Borrelia burgdorferi. Lipoproteins, all have cysteine here, and that is what's lipidated, form the lipoprotein. This shows the relationship between a large group of BMP proteins that differ quite substantially from one another. Within a group, within a family, and here's a small BMP family here, there may be only 70% amino acid identity. And then between families, there's as little as 30% amino acid identity. So this is a great deal of variability that's developed over the eons. Now, for the next few slides, I'm just going to summarize our findings of explaining in Borrelia hermsii and Lyme fever how this comes about. And this has taken a number of years, a number of people have been involved, and I hope I can do that justice with a few slides, but I think this will hit the high points. Basically, it's a fairly simple explanation that if you have the phenomenon of one antigen on at one point in time, and then a few days later another antigen is on, and then subsequently this changes, switches, as it were, over the course of a few weeks. It's basically like having a cassette player, and then you're having a bunch of cassettes up on your desk, and you just switch out the cassette. So you have one player, many different cassettes to put in the player, and that's essentially what happens. These are, this is a probe, a DNA probe for serotype 7 BMP gene. And you can see in these three different serotypes, each of them have a sequence, have that gene in it. But only in serotype 7 you have this extra copy. So this extra copy is essentially at the cassette player. And at this location it's produced, this other location is not. And this is another way of looking at it. These are the two different locations for the gene, which is shown in yellow here. This is a silent gene. It's not made. The arrow indicates that the gene is expressed. And although in the two locations there's a start code on the start of the gene and some of the signals for making the ribosomal binding sequence, at the expression site there's the promoter, which is essentially the cassette player. So that's how it happens. And how that comes about is by gene switching. For a more technical term is gene conversion. And you have an active site here on a plasmid, one of the linear plasmids in the Borrelia. And then you have silent sites, silent plasmids with silent genes on them. And if you switch those, essentially the silent site replacing what's there in the expression site. They don't really exchange places. An extra copy is made of the silent one, and that replaces the one in the expression site. Then you can change whatever is in the cassette player. And this can happen totally, also partly. Only part of the gene may change. There's another mechanism also that occurs, is that if some of these genes are in groups, in this case pairs, so there's one gene here and another gene here. The first gene is expressed, and the second gene isn't. There are repeated sequences of DNA between those genes. If you delete that out, and you form a circle, then if that happens, then the second gene in a row gets expressed. And something like that happens in Borrelia burgdorferi as well. Now this summarizes some things that can happen with Borrelia hermsii. Again, this represents a lot of individual experiments, but I think it gets the point across is that summarizes what I just showed you in terms of this two genes in a row, one gene is deleted out. Now the interesting thing that we found most recently is after that happens, after you get this deletion and then a new gene placed here, for a period of time, that new gene continues to evolve, it continues to accumulate mutations for several generations. And in fact, it goes on continuing to change. And if you just took this picture here, what I showed you, and showed it to an immunologist, they would say, well, this looks very familiar. In fact, that's something very similar happens with immunoglobulins. After you have formed a new immunoglobulin, particularly in birds, that the gene that's formed will continue to evolve and continue for changes to occur, which are called somatic mutations. Well, the Borrelia does the same thing. After a switch like that, they can continue to evolve and perhaps further avoid immune response in this way. So we found that one of the Lactobacillus bacterium strategy to generate diversity is actually a mirror image of what the immune system does to try to eliminate. So these organisms have developed various ways of, clever ways of defeating the host. I just want to spend a few minutes dealing with the issue of antigenic variation in Borrelia burgdorferi. You've heard something about that already. I think less is known about what's going on in Borrelia burgdorferi. Technically, it's harder to study. There are fewer organisms to sample in the blood. The issue of what happens in vitro and in vivo has been raised. But there are some things that are known, and I mainly will be concentrated on studies from my own lab for the sake of time. But it's known for a long time that OSB varies. And this is just growing OSB in the laboratory. taking various lines of it and seeing what happens. And clearly over time, with clonal populations, there are differences in the OSB protein and their reactivity. And one of the interesting things, and from my point of view still unsolved and important phenomenon, is this formation of a shorter form of OSB. This has been noted in vitro. There's some evidence that happens in vivo as well. The significance of this, of why the cells so frequently will make a short form of OSB, as far as I know, or at least for me, is unknown. Now, I'd like to take some issue with an earlier statement. There was simply being an emphatic statement by Dr. Barnhold that certainly OSB has no relevance in the mammalian host or the human host. And I'm not quite as confident with that. This is some data dealing with OSB, which really is a part and parcel, very similar, or really together with OSB. This was a study done by Willie Bergdorfer years ago, in which he can gauge infected cotton rats by ticks, not by people, by ticks. And then we cultured at various periods of time the populations as over time. And these are culture organisms. It may not reflect actually what's going on, but it clearly shows that some changes have been occurring in OSB. This, and I think it's a phenomenon that still needs to be explained, that it may not be quite so simple to say that OSB and B are not expressed at all in the mammal. There's other evidence that the humans make antibodies to OSB. The original clone, the OSB clone, is being used in one of the vaccine trials, and I was isolated, identified with sera from Dr. Edward Grunwald, Joe Lyme. And this was a patient, we used a patient who had Lyme disease. And there was a very clear and dramatic response to OSB and B. And most patients with arthritis, chronic arthritis of the joints, have a very strong response to OSB and or B. I'll just briefly show some other forms of what can happen with Borrelia burgdorferi. Is that very similar to the deletion that occurring in Borrelia hermsii, you get a deletion between the two range genes, OSB and B, a deletion between those who directly you get a truncated chimeric protein. And also you can incubating the organisms with antibodies to OSB or B or polyclonal to a number of different antigens, you can completely eliminate the plasma. In this case, it's a 49 kilobase plasma that carries the genes for OSB and B. The cell will continue to live, in vitro at least, without that plasma. And in fact, it will live without any linear plasmids at all. And depending on the type of plasmids in the cell, determines, to some extent at least, the expression of OSB and B and OSC. So this is as you can see here, a cell that doesn't make any of the major surface proteins. And here's a cell here that makes a large amount of OSC and not OSB and B. So there can be a lot of variability in what's expressed in vitro as well as in vivo. Now, just going to finish out a few words about the other phenomenon we're studying, is about Borrelia burgdorferi and its entrance into the brain. And showing here the Galapagos Island, and this is, I'm sure somebody recognizes, Galapagos Island is famous in one respect for the study of evolution, because Charles Darwin went there to describe these finches that probably arrived at Galapagos Islands long ago as maybe a founder pair, and then all these different types of finches developed there that are not seen anywhere else in the world. It's all that's happening on Galapagos Island. So it's very similar to what happened to Borrelia hermsii. One cell in an animal, and it continues to evolve in these different forms. So that's all right. The important thing about that is not only just showing this occurring, but the beaks. Charles Darwin and others since then have concentrated on the beaks. So these are not just to be for aesthetic purposes, they have a function. You can look at these different bees in terms of their function, which is early structure function studies. And you can see that a certain bee applies to do certain sort of things. And we've taken the idea that perhaps these BFDs or these proteins have a function, they're not just there as antigen. And what are they doing? And one study that a young physician in our laboratory carried out was infected some skid mice, beneficial mice with Borrelia turriticata. And we use that because in the literature, Borrelia turriticata frequently causes neurologic disease that in many respects is identical to Lyme disease. You look at the old literature and you can't find any difference between what's described in Borrelia turriticata infections and many of what happens with Borrelia turriticata. So he infected this one particular mouse, and over time, without any antibody response, he evolved into two populations, starting with a single cell. Year one, population was found in plasma, at 100 days and one in the brain. These cleaved off by protease to show that they're OS proteins or BMP proteins, surface proteins. And there are some interesting biologic differences between these cells. The serotype B cells, if you take the population that affect other skid mice, cause arthritis. This is joint size at day 14 here. And serotype A cells do not tend to do that. Degree is control, DBS control. Serotype B cells kill baby mice. Serotype A cells do not. All baby mice are fine. Not surprisingly, there was a difference in the number of organisms in the mice. Down at the bottom here, these are the number of organisms in the blood. Down at the bottom here is serotype A, and more than 10-fold higher is serotype B. So these were, again, I want to stress that these came from a single cell originally, that they're isogenic in all respects from what we can tell, except for the surface protein that they make. And this determines the amount of organisms in the blood. And here, looking at that again, Diego infected mice with combinations of serotype A and B, put those in mice, and then later looked at the plasma and the brain, and only serotype A was found in the brain, and in the plasma there was both. A curious thing, though, is why we knew from immunosuppressants that there were approximately equal numbers. In fact, there was more B in the blood than A. The previous slide demonstrated that. So why here in this culture was so little serotype B present? Well, it turns out that serotype B grows very well in the mouse, but it doesn't grow very well in culture. It lags behind serotype A and grows less in it. So it really depends on the environment in which you find these cells, which their biological characteristics. And this just summarizes some of the characteristics we can infect with one cell, with both A and B. A doesn't grow as well in vivo, but goes better in vitro. A penetrates monolayers, endothelial, brain endothelial cells better than B. B causes arthritis and kills mice, but does not invade the nervous system. There are these differences in function. And just to summarize and bring us to a close about our view of this, that we think that invasion of the CNS is a very important part of the pathogenesis of chronic Lyme disease. It's not the entire explanation, but I think a lot of these things might, if the organism is persisting there, it's not being eliminated by the immune system. Certainly that's an explanation of why antibiotics in some cases may not be effective. And this just acknowledges many people who have been involved in these studies. I probably want to point out specifically Diego Cadavid, who is now at Georgetown University and is a neurologist, working with Andy Packner and one who's struck. And thank you. Okay, the next speaker will be Dr. Janice Weiss at the Tom, part of the town volunteer. Janice will speak about the correlation of severity of arthritis or level of persistence of spirochetes enduring Lyme disease.
Thank you. Can you hear me? And I'd like to thank the organizers of the Lyme Disease Foundation for the opportunity to speak today. And I'll try to get through my talk without another coughing attack. Can somebody maybe center the slide on the screen? Thank you. So my laboratory studies the animal model of the mouse model of Lyme disease, a study developed by Steve Barthold and colleagues in order to understand the aspects of infection and inflammation which are related to arthritis development. And in this model, mice of the C3H strain develop much more severe arthritis when infected with the N40 strain of Borrelia burgdorferi than do mice of the Val C strain, which develop mild arthritis. Now, our goal is to understand the inflammatory events which would result in severe arthritis development in the C3H strain. Now, many aspects of the inflammatory response to Borrelia are directed by the response to the stimulatory properties of the outer surface lipoproteins. And I'm just going to summarize data from a large number of different labs who studied the stimulatory outer surface lipoproteins. Macrophage responses stimulated by the lipoproteins are production of inflammatory cytokines, nitric oxide, and other inflammatory mediators. Endothelial cells will produce adhesion molecules, chemokines, and cytokines in response to these lipoproteins. B cells will be induced to proliferate and produce immunoglobulin, its